Greetings, Earthlings. Welcome back to my channel, the onlylaurenarnez channel. We have a nice, cozy fire, and I am your professor, and I'm here to give you today's lecture. Today's lecture, of course, accordingly, as natural as it shall be. As natural as you want it to be. What can I do at the end of the day? Okay, so let me not long in that intro. Today's lecture and today's topic is Physics Friday! Yeah, woo! But today we're going to be doing material sciences for those who are into crystals and crystallography, and we're just going to be taking this straight out of the chapter of my materials science book, which I never bought, and we're going to be exploring a little bit of the concepts. I'm going to be sharing them with you as I read them, and I'm going to give you the interpretation as to what they mean. And this is the most basic part of material science. So for those who want to investigate this, the name of this book or buy the book, it's called Introduction to the Physics and Chemistry of Material. So there are structures of matter, as we talk about today. So these are basically talking about the basic building blocks of the materials in the material world. Now this is how the most basic of the fundamental building blocks are formed. Every material has a structured pattern that is built on, and the structure of the material is generally determined by the size of the atom as well as the ion of its constitutes by its bonding between them. So 5.1 talks about the structure of metals. Now, as you may not know, but metallics tend to have a crystalline structure. Because metallic bond is non-directional, and because the positive ion cores attract each other through intervening sea of electrons that flows between them, metals tend to form closed packed structures, meaning they try to come as close together in order to organize or maximize the condition of their structure number. Well, their coordination number. So this means that they like come together kind of closely so that they can get like basically like electricity can run through them bros very quickly, basically. And then there is the difference between face-centered cubic structures and hexagonal closed packed structures. This is gonna go over your head because it went over my head when I took the class, but just bear with me and take notes always. So basically, subjecting elements to high pressure alters their internuclear distance and makes P minus V, that's pressure minus volume, contribution of free energy, which can produce solid state phase changes. The only simple explanation to this seems to be that one phase that happens to have the lowest free energy under ambient conditions are the ones that appear in figure 5.3. Let me show you 5.3 really quick. Can you see that? That's figure 5.3, and I'm just going to show you what these structures look like. These are the basics of what this is. I think this is obviously a closed packed structure, and this is the more of a looser packed structure, the hexagonal structure. Wait, no, is this the hexagonal structure? Well, this one is the high planar density atomic configuration of 111, and this one is the projection of the 111 ABC planes on the 110 face. So let me just kind of say this so this doesn't seem like confusing. So the reason this is important because electricity, electrons and photons and different types of molecular atomic things have to run through these structures. Now, like light would come through here, bounce off this part, and then maybe go through there, and that kind of thing. That's why it's really important to be able to understand this crystallography. See, this is a cubic lattice structure. This is what we worked on our project, as far as our project goes. And this is just, it's a simple cubic structure. It is rock salt. It's not like quartz crystal or anything like that, so it just has a simple building block structure with these building blocks on either side and the molecules in the center. And this is an FCC with the counter anion occupying all orthohedral sides, and the lines are the ionic bonds between them. And so they go in, this is not a quartz, this is a quartz, it's a tetrahedron, which is what a quartz crystal as far as a structured matter goes. If you didn't know, then now you know that quartz crystal is the way they keep up with the accurate time, because how does that work? It's able to keep time more accurately than the atom clock. So it's like, okay, let me explain this in scientific terms. Basically, the ionic bonds between the molecular structures are accurate or equivalent to that of time in reality, if it makes sense. So not all these structures have the same crystallization as the time in our reality that we live. Okay, so this is something they're not gonna tell you. I'm gonna put you on game. Okay, so they be pretending like it's something else, but this is what it actually is. Okay, so the quartz crystal is in sync with the time that we live in, the days of the months of the years of the seconds of the hours of the days, blah blah. So when you run your particle through it, it keeps accurate time. And I don't know what particle they use. It's probably electricity, an electron or something, whichever one of them energies that they use. So that is just a touch of materials science. What are your favorite crystals that you like? Because I know people do the crystals, they charge the crystals, the third eye of the chakra. Anyway, like and subscribe and share this video and buy my book Quintessence. Goodbye everything.